um, same as yesterday, so that we can go ahead and get started. So last round we were looking at sampling and at working on doing a survey. Surveys are just one form of statistical study. A lot of times, and we see this in the pharmaceutical industry, especially, where we do a lot of basic research and accumulate data. But it's the same sort of thing. Our questions are just different, and we have to ask our questions very carefully and design our study to give us meaningful answers. Also, you should never be doing a survey or any sort of study without a goal in mind. What are you trying to learn? And how are you going to design the study to give you that answer very, very clearly? I've got a presentation that I'll get into in a little bit about that. But let's look at some more of the definitions. And I've been trying to scan in my definition sheets, which I will finish when we're done with this class and email them to you guys. But we'll go through some of these definitions now. Looks like we have one other person on board. Is this Candy?
Yeah, it's me.
Okay, great. Welcome to class. I was just getting started on looking at some more definitions, and so one of them is when you're doing some sort of study, especially when we're doing surveys, a simple random sample is that we select our subjects in a way that every possible sample of the same size has a chance to be chosen. In other words, everybody that could be a part of the study of our population that we're looking at has the same chance of being included. The distinction is the sample of the same size n, every possible sample, which means if you've got 100,000 people and you want to survey 1,000, every single possible variant of 1,000 members has the same chance of being chosen. So in reality, that is very, very difficult because random sampling methodology is actually non-random in many ways, because there has to be some method by which we select. But we do our best with this, and as is the case with all of these things, we do our best to do that. So basically, we want to use those sampling methods as random as possible. Why do we want random? Because random is one of the few ways that we can remove as many sources of bias as possible. If we are choosing non-random, then it's very difficult to prove that you haven't biased the sample. One of the most common non-random choices is what we call a convenience survey. That just means that we go and talk to our friends. and the people we're associated with. That is not random. We may randomly choose which of our friends, if we have a big enough database of friends, to include, but they're biased in that we already know them. And we already, we've limited our sample size. So it's not possible to scale up the results to the total population. So we have those kinds of things. So let's take a look here. So with our random sampling, we can do this by doing either picking out some number. These are telephone numbers, I believe. So generally, the computer uses a randomization program to select these numbers that you're going to call to be part of this survey. And again, the problem is that computers, it's impossible to get true random in a computer because a computer works on algorithms. Algorithms by nature are not random, okay? Then we have systematic sampling, sometimes called the mathematician's way, choosing every third person from some starting point. Or every 50th or whatever. This is done a lot of times in quality assurance and quality control procedures where you're producing material. We do this in the pharmaceutical industry when we're making a batch of a drug, and we're probably doing a million capsule run. We may choose every 10,000th and pull it out for analysis to be sure that the procedure is running as it's supposed to. And we also set these things aside for testing at various intervals during the next several years to make sure that the product remains the product that we say. It doesn't deteriorate. So this is usually done by some sort of systematic sampling, which is, as long as that systematic sampling is maintained through the entire run, is not a whole lot different from random, especially in a manufacturing. We've got, I talked about convenience sampling. Either our friends or people walking by on the street. Many of these street side sampling surveys that you see, especially this time of year around election time, is convenience sampling, because all you're doing, we go to the Chilson Center in Loveland for exercise and that sort of thing. And during this silly season, there's always somebody out in front saying, "Can I get you to do a survey?" So that's a convenience sample, because again, it's people walking in, and they're people that are not random because not everybody goes there. Stratified sample means to divide the population into different subgroups or strata layers, so that the subjects will share some characteristic, and they use gender or age. It can be anything you want. It can be we can do that as well. But anyway, we choose that, and then we then draw a sample, trying to be as random as possible from each group. And so in this case, they're talking about Democrats versus Republicans, and we see a lot of that in the sampling these days. And there's something called cluster sampling, in which we divide the population into sections or clusters, and then take all members, do a census of the members from those selected clusters. Here they've got classes at a college. We can also see it by dividing looking at the at like wards. I mean, the city of Loveland is divided into 4 wards. And so those can be clusters. They can also, you can cluster it by neighborhood. You can cluster it by zip code. You can cluster by a lot of different ways. But the issue with cluster sampling is that when you do that, you're assuming that the totality of the clusters reflects the broad population of whatever you're doing. In a college, that's true. They're all college students. In a political clustering, that isn't true because, of course, there's a very great difference between neighborhood and neighborhood in terms of economics, in terms of ethnicity. So we see a lot of those different kinds of things, but that's another method of doing the sampling. So when we do that, we want to make a distinction here between stratified and cluster because they sound similar. But remember that cluster sampling where actually does a census from a randomly chosen sample of your clusters. So if we're in a large city, let's just take the largest in our region, Denver, where we have lots and lots of wards or the equivalent of wards, where people live, we have a lot of choices. In a city like Loveland, we have 4. So it probably cluster sampling in a city like Loveland is not a good idea because I can guarantee you that the economic factors here in Loveland are exaggerated because the people with more with higher economic status, I hate that word, but I don't know a better one right now. But people at the higher economic levels generally live in very similar areas. So we don't want to make the wrong choices here. It's very hard in a city of roughly 80,000 divided into 4 wards. If you're going to do a census population, that's going to be an awful lot of people. So we would probably use some form of stratified or even a random sampling based on addresses. These days, phone numbers are not a good idea because we all have cell phones and we've kept the number from wherever we are. So we've got people with numbers from all over the country. So doing phone number searches is probably not the best. Okay, it's probably not the best idea. There is something called multi-stage sampling, and we look at sorry for moving this thing up and down so fast. My computer is being very sensitive this morning for some reason. So we use different ways of looking at the sampling that we do at different stages of a study. For example, that they give here, one multi-stage sample might involve random selection of clusters, but instead of surveying all the members of the clusters, you might randomly select some number of people out of each cluster. So you begin with cluster and end with stratified. So that is can be very effective, but it can be very complex, and so we don't do that for a lot of things. You wouldn't do that, for instance, looking at the school, and the the confound it, what happened? Okay. So the unemployment statistics are based on households. It's impractical to really visit each member in a simple random, because individual households are spread all over the country. Instead, the Census Bureau and the BLS, the Bureau of Labor Statistics, will collaborate on a survey that they obtain fairly often, a lot more often than the decennial census. So we look at very simple few questions: unemployment rates, college enrollments, weekly earnings. In this case, they talk about looking at these primary sampling units that they've defined. There's 2,025 of them in the U.S. Metropolitan areas, large counties, and combinations of smaller counties. So we have geographical connection, and it allows us to look at regional differences in these factors. So this so then they break it on down from there. So these are complicated things that you probably will never see, but it is an interesting structure in dealing with a very, very large study, that we can expect to see regional differences, and unemployment and income and so forth are going to be very much regional. When let's take a look at these kinds of observational studies. We need to look at, are we looking at a retrospective study? In other words, we go back in time and collect data over a past period by going into records and that sort of thing. Do we do what we call a cross-sectional study, where we look at data measured at a single time point? I hate the phrase point in time, but at a single time point. Or prospective study, which is also referred to as a longitudinal or cohort study, looking forward in time to observe groups. One of the most famous of the prospective studies is called the Framingham Heart Study. This is a study that's been going on for now 60 or 70 or even maybe 80 years in Massachusetts, following, looking at heart disease, and now it's been expanded to other areas as well. But it started off looking at heart disease in an area in Massachusetts where they were looking at lifestyle choices and so forth. This has been going on for all this time. It's been has been a major factor in medical research. But that's definitely a prospective study. Going back and looking at, say, population growth and population dynamics, looking at an area, what has been the population dynamics of, say, the southeastern United States over the last 100 years. And so you'd be going back and looking at the data, how many people, what kind of work they do, and so forth in that area of the country. That's a retrospective study. And then looking at current statistics such as average incomes and unemployment in a specific region of the country. This would be measured today, because of course it changes over time. So when we look at a cross-sectional study, we're interested in what it is today. We may compare that with retrospective data to look at the total picture of population dynamics, and use that to and looking at those past changes versus the current, and then making some predictions about what the future will be, and then follow that in a prospective way. So this is done a lot. Statistics are being gathered all the time. So let's go back and look at one of the largest public health efforts, and it turns out to be an effort that I go back and I find myself having been a part of, the Salk vaccine experiment, which was done in the early 1950s, where where 200,000 children were given a treatment consisting of the injectable Salk vaccine, and a second group were injected with a placebo. This would be a hard study to do today, but in the 1950s, where things were a little looser. But we looked at the effectiveness of this vaccine during the major polio epidemic that was going on at the time. We were able to prove that the vaccine was effective. So what happens is that children were randomly assigned to treatment or placebo group, and I don't have any idea if there was parental approval on this. If we had to, the parents had to sign off on this. This is too long ago. But what happens is nobody was supposed to know who got what, especially the children didn't know this, and their parents didn't know this. So we randomly did that to prove that we could remove bias from the study. So we have to look at all of at all of the methods that were used to do this in order to prove that the vaccine itself was effective in preventing polio. Now these numbers, 200,000 people in basically in each group, basically 201,000 in each group. 33 children given the vaccine developed polio, and 115 given placebo. That was considered a pretty significant difference, and it indicated that the vaccine was effective. Now we've improved the vaccine since then, and the oral vaccine is even more effective than the injectable. So this was a huge study in the 1950s, and it was difficult to do because, of course, all we did was assign children to two groups, looking to have the two groups would have similar distribution of age, etc. But it was something to try and make sure that the groups were matched, and it would not, this is difficult to do in people because, of course, people are so different, and we now know that lifestyle and diet and other things have a tremendous effect on the propensity for disease. There is a replication is another issue. We want the study to be designed such that that if the study is repeated, we're going to get essentially the same results. But large sample sizes are what we were looking for in terms of the result. So blinding is another important thing when you're doing doing studies that are to give a scientific result. We look at blinding. Blinding is when the subjects do not know whether or not they're receiving treatment or placebo. There's always an issue here of ethics. There are some kinds of studies where blinding is unethical. Basically, studies such as many cancer drugs are not blinded because we're actually trying to study the effects of a drug to cure a very an incurable disease. So there are some times when that's not legitimate in medicine, but what we're trying to do is when we blind, we are trying to eliminate what we call the placebo effect, which is when someone thinking that they're getting a treatment are biased to believe that they're getting better. With things like cancer and other kinds of diseases that we can actually measure the results. This is not a major problem, but when we get into certain kinds of diseases and like depression and anxiety, placebo effect is very, very high, and we just have to recognize that. The other thing that happens in medicine is a double blind, which means that neither the subjects nor the investigators knew who gets what. And why do we do that? Well, investigators have their own biases, and they're going to see if they think that their patients are getting the drug, they're going to see improvement when it doesn't happen. And if they believe their patients were getting placebo, they're not going to see any improvement in the disease when it may in fact occur. In fact, we even go further with that now, and I'll just tell you how we do things now in major clinical trials, is that the blinding that occurs is also blind to the study sponsor. We have a group we have an outside group that does the coding. All we know is that we send out a drug for patient X, and that's all it is. We just know it's drug for patient X. So the patient doesn't know, the doctor doesn't know, and then the sponsor doesn't know. Again, this is to reduce bias. And what happens is that we just know that we have groups of patients, and then we have a completely unaffiliated group. In other words, a group of medical researchers who are not involved in the experiment, do not work for the company, as what we call an advisory board, and they monitor the difference. And if they perceive that there is a group of patients who are getting better, they will break the code without talking to anyone else and look at the results. They can stop the study. If they see that there is a group that is actually getting worse, they can stop the study and break the code and then analyze the results at that point. So we try to take as much as possible of the bias. And of course, there's a tremendous amount of temptation, especially in something as valuable as pharmaceuticals, to bias, to see an effect that isn't occurring. That's why we do these completely unrelated people that are participating without without any direct connection with the experiment itself or with the sponsor. So we have to design our experiments in a way that that will give us the least possible bias. Okay. So interrupt me with any questions you may have. Okay, so here you can look at this in the elementary statistics text, the Triola text as well. But experimental design would be to treat all of women subjects or give placebo to all men. Completely randomized is to treat randomly selected patients and then give others placebo. A randomized block design, form a block of women and men, and then or do matched pairs. The typical matched pair kind of design is twin studies, where you're looking at the differences in some factor in twins. And again, when we do this, we have to recognize that there are different kinds of twins: identical, mirror, and fraternal twins. So also twins that are raised together versus twins that are raised separately. So there's a lot of things that you have to take into consideration. You might just be looking at siblings. You might, but one way or another, you look at these matched pairs so you're getting measurements from them before and after a treatment, but there are lots of different kinds of matched pair designs. So there you can read through sampling error. The issue is that sampling error occurs when the sample has been selected with a random method, but there is a discrepancy. Sometimes this happens. Truly proper study design can eliminate this. Human error, wrong data entries, computer errors, et cetera, biased wording, false data. This is why we try to make sure that our data is verifiable. And then we have biased conclusions or using statistical methods that aren't appropriate. Again, non-random sampling error comes from using voluntary response or convenience. So when we're looking at doing a study, we have to look at how we're going to get the data. So let's move past this problem set. And then let's go to chapter 2, which is about how we present data. There are lots and lots of ways of summarizing data. Let's look at characteristics, and we'll see some of these when I finally get the definitions to you. The center is the middle of a data set. There are a couple of different ways of looking at that. You can do a numerical average. or you can take if you order the data in some way, lower to higher, higher to lower, in some fashion, you can take the piece of data that's in the exact center of the distribution. Okay. Variation means how does the data vary? We'll see that data will vary across a spectrum. Sometimes we have very tight sometimes we have very tight data, meaning that the variation is across a very narrow range, and sometimes we have very broad variation, meaning exactly that. They vary over a very broad range. The distribution is the nature of the spread. You've all heard the bell-shaped curve. In a normal distribution, you're going to have most of the data being concentrated in a narrow area of a bell shape, and then we'll get samples at the extremes. Outliers are sample values that are very far away from the vast majority. I mentioned football coaches, college football coaches' salaries in the last lecture. Because they're a good example. We have a few that are way higher than what we would consider the bulk of the data. And then there are, we look at changes over time. So the critical, so we want to look at interpretation and use a lot of critical data. And we have to look at changes over time, and this sidebar here is a good example. 100 years ago, and I think this book was actually written just a couple of, this edition was probably published just a few years ago. So let's take this back to about just a little bit further to just before World War I. So we have these numbers, and things have changed today. Today, virtually every phone, every house in the country has a phone. Essentially, all of them are going to have bathtubs. You have somebody living completely off grid in the mountains of Montana, might not. Life expectancy, 47 years. Today, it's 74 for men and a little higher for women. Mean hourly wage, 22 cents. We're talking about trying to raise, and in fact, I guess next year the minimum hourly wage in Colorado is supposed to go to $12. About 230 murders in the United States. We won't talk about that topic. It's too emotional. So let's take a look at a couple of ways of looking at data. And let's get rid of that, okay? Frequency is the number of, we generally want to place our data in what we call classes. In the case here, good one here is IQ scores, 50 to 69, etc. So in basically 20-point ranges. The frequency just counts the number in terms of a population. So we've got a number of patients here, 35, 70, 78 measurements in this particular group. 2 of them had IQ scores between 50 and 69, and these are groups of people with low levels of lead in their blood. So we have 70 to 89, 33, 90 to 109, centered on that 100, 35, so the largest group. And then as we go higher, it falls off. And note here that we have these lower, these classes. There are a couple of things. The limits, the lower class limits are 50, are values of even multiples of 10. And then the lowest number that belongs to each class is 20 higher. Now, we don't just subtract 50 from 69. That's going to make it look like the difference is 19. If we include the lower number here, which is what we have to do, and you count this up, this is a class size of 20. Boundaries are the numbers that separate the classes. So the boundaries are actually midway between the upper limit of one class and the lower limit of the next. So the boundary between this first class and the second is 69.5. And the midpoints are here. We simply add up the two numbers and divide by 2. So the midpoint here is 79.5 of this 70 to 89 group. Okay, and the class width is 20. Finding the correct class width can be tricky, and and we need to remember that this is the way we can graph it out. The class starts at 50. The first class starts at 50, ends at 69. The next class starts at 70. So there's a gap of 1. So the boundary is midway between these 2 points. So it's one way of looking at going out. When we say that the next class boundary above the top is 149.5, it's because we are assuming that the next class boundary starts at 150. We don't have anybody in there, so we don't report those data. So the frequency distribution is really literally, the frequency is the number of people in each one. So we can present this data in several different ways. I'm not going to go through how they chose the class widths. They decided the number of classes that they wanted, and then figured out how many people, what their range was, which ranged apparently from 50 to 141. So we simply took that difference and divided by the number of classes and then rounded it up to a convenient number. Could this have been 18 or 19? Sure, but it would have been an inconvenient number. So we just round those up. Here we have, the Connecticut, East Haven, Connecticut Police Department tickets that were traffic tickets that were given. So what we have is the interesting thing is that this data, let's just talk about how you can skew the results. During a recent 9-month period in East Haven, they gave out a lot of tickets. We've got 329, 344, 362, 366, 371 tickets handed out in this time. And the police classified the ethnic group of ethnic groups here: white, black, Asian, Hispanic, white/Hispanic. I don't know what, well, that's interesting that they used that, or no indication. It turned out that they claimed 329 were white, but 209 of the tickets had Hispanic names. for whatever that's worth. What use is such a bit of information? Well, it might be useful if you're looking at when looking at bias in giving tickets, and then by having, and by looking, and it may be that they're looking at the person and making a judgment as to what their ethnicity is, rather than worrying about the name. Of course, if you have if you have a Northern European Anglo person married to a Hispanic person, the name is going to be Hispanic. So this particular group makes me look at it and say, before you can draw any conclusions whatsoever, you need more data. And this is an example to me of statistics that are kind of useless because we don't really know what they mean. As I say, 209 could have Hispanic names, but what if they are married to a person with an Hispanic name and look white, and what's, so this is to me not a particularly useful table. On top of that, if you're trying to show that we're not biased against the Black population, we might take someone who is very light skinned and just call them white. So this is kind of not a fun, nice statistical study to me. It's an example of a study that has no real value. That's my bias. Relative frequency distribution merely is what is the percentage of the total. If we go back to those low lead data, there were 71, I think, total students. So what you do is you divide the number of people in the group in your cohort here, your level, by the total. So this would be, that number, which was something like 2, and the 50 to 69 is going to be 2.6%. So percentages are useful if you really deal with percentages well. They're a useful way of comparing the size of groups. They're more useful than numbers. And this is why you see percentages given, especially in political polls. We see these, in terms of political polls. Last night we were looking at the ballots for this election coming up, and we took a look. I went online and looked at the political polls related to ballot issues CC and DD, or Proposition CC and Proposition DD, and we had some polling data that said 52% of polled likely voters were in support of Proposition CC, and 49 plus, or 40, I guess 47% were opposed. So that gives you an idea. Of relative. Whereas if they just given numbers, they would have been meaningless. So cumulative frequency merely adds up the total number. So IQ less than 70. So what we're doing is we're looking at each of the levels and just sort of looking at adding them up. So the cumulative frequency means the total number of members of the study that were at each that were below the top of each of the levels that we chose, each of the classes. So in this case, we had, of our 78, 2 had an IQ of less than 70. 70 had an IQ of less than 110. And of course, all 78 had IQs of less than 150 because there was no one above 150. So the cumulative frequency ultimately adds up. The last number should be the total number of data points. Let's look at something that shows what we call a normal distribution. If we go through our classes, the frequencies will start low, they'll maximize out at some point, and they will decrease. Usually that point is going to be in the middle of our data set. That's what we call a normal distribution, is that it will start low, increase to a maximum, and then become low again down the curve. We call this, we'll see this when we do z-scores next week. So we look at data. This I'm not even going to bother with. What does a gap tell us? Okay, so this is a study of the composition of copper in pennies versus zinc, because in 1983, let's go back to the bottom of the previous page. In 1983, we changed from 95% copper and 5% zinc to 2.5% copper and 97.5% zinc. Okay, so then we see that randomly there's a big gap in the weight of pennies. We've got, if we just randomly select pennies from a pile that has a distribution of pennies from both pre-1983 and post-1983, we find that there is a group that has somewhere between 2.4 and 2.59 as the weight of the pennies. And then there's a gap until we get to 2.9 to 3.19. My guess, copper being much heavier than zinc, that this last three classes represent pre-1983 pennies, and the first two classes are post-1983 pennies. And it looks to me like there is a potential hypothesis that the manufacturing of post-1983 pennies is much more consistent than pre-1983 pennies. But that's only a hypothesis. Okay. So let's move on to the next page. We'll just back out of that. We'll look first at how we present data. Histograms are a common bar type graph. These are bars of equal width so as not to bias what someone sees in each of those. And they present the data for each class of one of these studies. So let's take a look. Here we have a histogram, and this is the IQ scores for the lead group. And this is simply the frequency. In other words, the IQ, the number of people with IQ scores in these ranges. Note that the boundaries are the boundaries between the classes. So we got 49.5 to 69.5, 89.5, etc. And all this does is tell us visually that there are a lot more people in these two classes than in the others. And the there's a relative frequency means that the percentages, okay? So here we have the frequency, these are the numbers, and the percentages. Those two presentations should look qualitatively exactly alike. In other words, there ought to be a low number in the first class, a high number in the second, slightly higher in the third, lower in the fourth, and then again much lower in the fifth, reflecting this. So in reality, they should, whether you use relative frequency or just the frequencies, should look exactly the same. Even though, okay, the ultimate object is not creating, but rather understanding. So let's take a look at this normal distribution. We talked about the bell curve. If we then take and do a little computer programming to calculate where these things start and make this a smooth curve, which it pretty much is, we find that the highest frequency occurs at the beginning of this particular class. So the bell shape should roughly mirror each half, but it doesn't center on a class. It centers on a class boundary. It should center somewhere in the data. So we'd look at this and say the data distribution is normal, or uniform. We can have skewed data if it's not symmetric. Okay. If we look at annual incomes of data here, get out of here. Please click this off. Thank you. So if we look at some of this, data can be skewed to the right or the left. We randomly say that skewed to the right is positive skew, and skew to the left is negative skew. So if we look at annual incomes, we have, if we look at annual incomes for across the country for income, if it were going to be a normal distribution, we'd expect it to look something like this. If it were uniform, which would be wonderful, I guess, it would look something like this. But commonly, we have the data is skewed to the right. So right skewed data is going to look like this, where we have the data being trailing off and much more data going to the right of the top of the curve, and skew to the left is here. Okay, let's move on. We can look at normality. We can look at several different things here. Let's look at, again, if we're looking at what we call normal distribution, is something that in a quantile plot, which really, we won't get into what that means, but basically it's a way to put the data in some sort of straight, in some sort of line position here. Normal distribution, then these things would be reasonably close to a straight line. Not normal, and reasonably close. Not normal is they don't at all. They've got numbers all over the place, and then these are sort of technical issues. I think we'll just move on. We don't have. Okay, we want to, okay. So interpreting a histogram, okay. The height, we've got sample size for height of people randomly selected entering the Natural History Museum. So we've got a cohort here of small people, short people, meaning kids. And we've got a gap here, an apparent gap where there is either 0 or close to 0 between 55 and about 57 inches. And then we have a group of people that range up, and then we've got this real outlier here at 110 inches, which is very much an outlier. So at this point, we look at this is what we call an outlier. So an outlier at 105 looks like about 108 inches. That is someone who is 9 feet tall. When we are looking at this, when we look at such outliers, we have a decision to make. Is it real data, or is it a transcribing error? Did someone really mean that they're 6 feet tall and somebody wrote 9 or whatever? We don't have 9 foot tall people. Yes? Okay. Okay. So we're going to skip through this. I just wanted to use that as an example. We can look at ages. We can do a lot of different things. Let's look at graphs that enlighten and graphs that can deceive. There's some material that is part of this text that we're not going to use, but we look at arm circumference and waist circumference. And then another is weight and pulse rate. And we've got these weight and pulse rate are examples of paired data, meaning you're looking at the weight and pulse rate of two of the same persons. If we look at the waist and arm circumference data, let's take a look at this, and we can roughly say here that that people with higher waist circumferences also have potentially higher arm circumference. This is not a real solid relationship, but you can see from this that it looks like there's a rough correlation. And there are lots of reasons. This doesn't get into the reason for that. It just says this is an observation. Whereas if we look at weight and pulse rate in males, this is a mess. There's no correlation here. Okay, let's just keep going here. And if we look at the pennies data, we've got clusters of data and a gap. Okay, so we've plotted this. There does not, but if we look at this here, the gap itself means that we're actually measuring apples and oranges, to me, because we're looking at pennies that have more copper in this particular group, or less copper in this particular group, so they weigh less, and more copper in this particular group, because we're looking at the year in which they were minted. So we're looking at that. So these, but there's such a scatter there that we can't really say anything other than there's no relationship between year and weight. Time series graphs are real common. We see this. Here's one of our favorites, the Dow Jones Industrial Average from 1980 at about 1,000, a little bit under 1,000, to 1999. Here, the year 2000, when it was up around, closing in on 12,000. And here after 2005, so it looks like 2007, just before the crash, 14,000. So we look at this, but we can't, there obviously there's a pretty clear correlation up until about 1995 or so, where we can say that there was a pretty consistent rise, and then it became chaotic. This is one of the problems that we deal with when looking at data. I don't want to go into, we'll go into plots another time, dot plots and stem and leaf plots. There's lots of ways of showing data. Multiple plots. A Pareto chart is just a bar graph where there's no boundary, but we don't have classes. We just have various kinds of data. I want to go to pie charts. Pie charts are a common method that we use to compare data. Pie charts can be useful, but the problem is that it's difficult to read these things, okay? What we have is, it's easy to see that various pieces of the pie are shown here for happiness, okay? This is a measure that's, kind of a squishy measure, but we can see that we get our most happiness from family or partner. And if they're done right, they go from largest to smallest, either clockwise or counterclockwise. But if this is set up right, but there is a limited ability to do this, and I'll get you back to pie charts later. Pie charts are kind of common, but they have some very great limitations. Frequency polygon is really just looking at plotting the number of data points between in a specific class, and just plotting that number and doing this. Again, it's a way of looking at normal distribution. And the relative frequency should be the same, look the same. Here we're looking at two different groups, high lead and low lead. Okay, so we have a slight, what looks to be a slight skew to the lower side. So we can compare two different groups using this to see how they compare. An ogive plot merely is the cumulative data, okay, up to, again, the maximum. Graphs that deceive using a non-zero axis is something that is really common. Here we're looking at highway fuel consumption here between a Civic, a Chevy Aveo, and a Toyota Camry. If we are looking at a graph that goes from 30 miles to the gallon to 36, then it looks like the Civic just beats the dickens out of the Chevy and especially the Camry. But we've skewed the look, because if we start at 0, which is a natural starting point, then the differences are much smaller. Clearly, if you look at this, the Honda Civic gets a little bit more mileage than the Chevy Aveo, and the Camry at 31, but this is at 36 to 34 to 31. So there is a difference here that is real. It does not take into account many other variables, and this is why it can be misleading as well. In general, a Honda Civic is a bit smaller and lighter than a Camry. So, and are we talking about a Camry with a 6-cylinder engine and a Civic with a 4? There's differences in efficiencies there. So there are many ways to mislead. We have also drawings, pictographs. Looking at this is a great one. Revenue passengers carried by airlines in 1984 and 2010 by looking at the size of an airplane being drawn. But if you look at the actual numbers, in 84, they carried 345 million passengers, and in 2010, 706. So it about doubled. But this looks like much more than just double. If we look at the size here, it's at least triple. It doesn't do a great job of depicting the data. It looks like there's been a very much larger than just double. And in fact, if you look at the volume here, this plane on the right is about 8 times the size as the plane on the left. So it's very misleading. Pictographs are awful. If we look at a different way of looking at it with a bar graph, then we see that this clearly is only about twice as large. So we want to be careful with how we present our data. Let's see, okay. I'm going to stop here with that because I really want to bring up something that has a different share. Do you have any questions, either of you?
Not at the moment. Well,
Okay.
actually, I think I might have asked this already. The assessment we're taking is it based off of this book or the other book?
It's going to be a mix. It's mainly based off this book,
Okay.
but you do have access to both. Okay.
Okay, thanks.
Okay. So I want to go through, this is a presentation that I had a chance to see about statistics and about misuse of statistics. Okay, we've talked about data collection, that we have to be careful with that, and presentation. So why do we use them? Well, we use them to really make decisions. To support hypotheses and so forth. But statistics should be a decision-making tool. Is something real? Is it fake? Is it valuable? We have a use for that. And in scientific research, it provides us with a framework for evaluating that can be as unbiased as possible, in evaluating the data that we've acquired. And so we need to be we need to find objective ways of doing this. So they can be misused. They can be misinterpreted. They can be misrepresented. We've already seen what altering scales on a graph to change the apparent values of the data by removing data that either doesn't support our hypothesis or seems to be way low or high based on anything else. there has to be a reason for excluding. We looked at the museum visitors, and we had a 108-inch tall person. That would be one that we could remove or explain and ignore simply because a 108-inch tall person just doesn't happen. So it is clearly a mistaken piece of data, but we have to be able to justify any data that we toss out. And we need to remember that we are looking at almost always looking at that factors that are not in a vacuum. So there are other variables that we need to find a way to explain or control for. And also to correlate. We just don't want to try to correlate things that don't have any relationship. And correlation is when we're looking at something like statistics on the frequency of colds related to weather. There is a definitive correlation there. We see that, and we know why that occurs. However, as I said last class, there's a wonderful study that looks at the correlation between subway fares and price of slices of pizza in New York. They do not cause each other, and what we're looking for is finding causation, and that's a difficult one to deal with, and we'll deal with it later. I love this. We all know that there are three kinds of lies: damn lies, and then statistics, because we can use statistics improperly to prove all sorts of things. I love this statement. 79.6% of all statistics are made up. How do we know that? Well, it's just a joke, obviously. But we can use misleading statistics and selective choosing of our data to bias the results. Often this comes inappropriately or inadvertently with people who are inexperienced with statistics. And my main thing here in class is to have you really be able to look and determine whether or not any sort of statistical statement has a basis to it, and to be very skeptical, especially of social and political and advertising statistics, okay? Because there are plenty of ways we can use statistics inappropriately. The misuse can occur when something clearly false is being asserted. They may result from mistakes, and mistakes can be very much inadvertent, or they may be misusing. And in some cases, and we see this to looking at intentional misuse. And what we need to do is anytime we see something that looks odd, we need to ask ourselves, is the person making this statement getting something out of this? They can occur when the person may know the material well, what we call a subject matter expert, but they don't understand statistics, and vice versa. A statistician who's looking at data without being an expert. The great one was the Atkins diet example we had last class, where there were these nice statistical findings, but they really had no practical value. And then, of course, if we've poor study design, not really looking at defining what we're studying, or just bad data. Apples and oranges. This is another great one. Broccoli has significantly less fat than the leading candy bar when looking at these things. Obviously, the answer to that is, well, yeah, so what? You know, if you're trying to be, to encourage people to use broccoli as a snack as opposed to a candy bar, depending on your group, good luck, but you know, that may be your point. Graphs, look at this pie chart. This is utterly useless. In fact, I think this is having to do with the portion of the market that any one brewery owns. And of course, you know, this is beside the fact that it's not arranged in ascending or descending order. It's just there are too many colors and too many things. This is utterly useless as a graph. So we often will use what we call data mining or data fishing, where we are going through large volumes of data to try and find relationships. And unfortunately, the more data you have, the more likely you are going to be finding relationships. And it really isn't a good practice to do that. You're not likely to be involved in that. Here's another one. When we're misusing statistics, we're looking at a study of 18 measured items, and in this idea that we're supposed to eat chocolate. But we're only having 14 subjects, and we're looking at 18 different parameters in each of these subjects. So the chances of finding some significant result skyrocket. By significant, what we're doing is when we define significance in statistics, we say that that there is a we're saying that there is a 5% chance. There's only a 5% or less chance that a difference between the data sets actually is real. And there's ways to calculate that. We'll get back to that. With 18 measurements, it turns out there's about a 60% chance of getting something significant. So we want to be careful about the number of things we're measuring. This is one of the problems. When you measure too many things, you're going to get in trouble. You also, from too many subjects, for measuring 18 different items, we're going to need, you know, hundreds, if not thousands, of subjects to get any useful data. We have to know what we're after. We have to know what it is that we are studying in order to properly interpret the statistics. And we should not be interpreting our own statistics in many cases. Correlation is a relationship between two things. Causation is very specific of one thing causing another. Let's just see as an example, data show that gray cars are statistically involved in less accidents than other colors in a particular city. It might be attempting to conclude that gray is a safer color. However, there are other factors that we need to consider. One, people who buy gray cars may be more conservative in their driving habits. Gray cars may tend to be and more prevalent in certain conservative model types than smaller or non-gray flashy cars. Here's another beautiful example. A study found in a particular area there is a correlation between an increase in car accidents in a month and increase in bear attacks during that same month. You know, I love this cartoon. This is why you don't bring a smart car to bear country. So the problem is, of course, rationally, car accidents don't cause bear attacks. So, you know, this is the kind of flawed correlation. I mean, yeah, okay, these things happen at the same time, but it does not mean that they cause each other. Also, we need to use the right technology and the right data, because the old thing we know, garbage in, garbage out, bad data is not going to give you, even with a very good model, isn't going to give you a good result. Likewise, good data with a bad model won't give you good results. So we have to do that, have to match those. Bias, simply prejudice. Bias happens from many reasons. Strong opinions, some benefit from the result, or you know, an attitude. This is something always worried about in various industries. You're completely free to carry out whatever research you want, as long as you come up to these results, these conclusions. And we've seen that. Again, we can look at presentation. We talked about this. Another example is using a three-dimensional pie chart. That's very misleading, because you concentrate on this thickness rather than what's there. Plus, this really ought to be in size order. So, and again, we got back to the difference in number of and by choosing the axis, a non-zero starting point on our axis. Again, another good example, biased scaling of these bar charts. If we look at the data here, we don't see a real big difference between all of these, whatever they are, whereas this looks really different. But if we look at where it starts versus where it ends, then we've skewed the data. So you have to be always very careful. Again, this is biased scaling, not putting any scale. So we don't have any idea what this one looks like. There's a real big difference. If you look at these two numbers, you're going to see, you're going to be able to say, no, that's not big a difference, that big a difference. And again, choosing our scale, these are based on the same data. We're going here from 2 to 10 and showing starting at 0. And here we have divided it and have the same size, but half the data. And graph C uses, again, the same data, but we have a very expanded y-axis here. So this makes the data look much flatter. So it, again, depends on what we're trying to say. Faulty polling, loaded questions, leading questions. How cold is the room is a bad question, because different people are going to give you different answers. What's the temperature? That is a much different question. The loaded questions force people into an answer that doesn't accurately reflect. The question directs, where do you enjoy drinking beer? By answering the question, they're saying they drink beer. However, a lot of people don't drink beer or any alcohol at all and cannot answer that question. That's a loaded question. First off, you have to determine that they actually do. And then if they don't, then your next question doesn't happen. double barrel questions, 2 questions in one. So you can't get meaningful answers. Are you satisfied or dissatisfied with pay and benefits? How do you answer that if you like the pay but hate the benefits, or hate the pay but like the benefits? You can't. Bias sampling means throwing out data, or picking very carefully where you acquire your data, and then not not using it. Here, this guy is didn't like the sample, so he threw it out. Famous example is the discovery of penicillin. In the research lab, the senior scientist, Alexander Fleming, had gone off on vacation and his graduate students were there. And they were studying the growth of bacteria in open petri dishes, which was the common method at the time, in a lab that had no screening on the windows. And the lab next door was dealing with molds. And graduate students came in, found mold in petri dishes and threw them out. Said, no, we're not gonna, these are spoiled, threw them out. And then Fleming came back and said, where are the petri dishes? And they said, well, they were spoiled, so we threw them out. And he said, I want to see them. And what he discovered was that the mold had inhibited the growth of bacteria on the plates. He recognized that there was something there that was stopping bacterial growth, and that led to the discovery of penicillin. So throwing out samples can cost you. Okay, so we're going to quit there. And I'm going to go back to here. And let's look at, we were supposed to do.
Question.
Yes, go ahead.
Are you going to give us that document you were just showing us?
Yeah, I can do that.
Okay, thank you.
Okay, let me make a note. It's a PDF, so I'll attach it to an email. Okay, I'll do that. We were supposed to do an in-class activity, so what I'm going to do is make this an assignment. So just quickly, I would not spend more than an hour really on this, to be honest, but I would like you to do this. That's what we would spend in class. Find a presentation or interpretation of statistical data that's bad. You can do this by a lot of ways. You can look up misuse of statistics or bad statistical presentation. You can do just basically a search like that, and you'll come up with a number of different things. Pick one and explain it, say why, how it's misleading, and what would be more accurate, okay?
Isn't that one of the questions in our assignment already?
That is part of your, this will lead you into your, as a way of getting started on your discussion. So this is really finding something and doing that. We would have done this in class and it would have been a little different from the discussion, but you can meld the two basically, okay?
Okay. Wait,
Okay.
so what did you want us to do related to the graph again?
Find something that presents data in either a misinterpretation or misrepresentation, something confusing, something that doesn't say that. There are lots of examples, believe me.
Okay.
Okay.
Mm-hmm.
Okay, let's go back quickly and look at the modules. So this week, the discussion, the misleading graphs assignment. So this is really a sort of a mix of the in-class activity and the week 1 assignment. And then you have your assessment. Okay?
Okay.
Any the misleading graphs is actually, you've got, if we look at that again, remember you've got a document and a spreadsheet to use. So this is a little different. So you're looking at something outside of this, okay, for the in-class activity. That makes sense?
Yes.
Okay. So any other questions?
Nope.
Okay, then we'll cut this off. Crystal, when you read this, I want you to send me an email with the word Luzon, Luzon, in it to let me know that you've listened to the presentation. All right. So I'm going to end this now, and I will have you guys stay warm, and I'll see you next week.
All right. Have a good weekend.
Thanks, you too.
Thanks. Have a good one.
Okay.